Right now, above our heads, massive currents of water vapor are moving rapidly across the sky. The strongest of these currents carry water roughly equivalent to 7.5 to 15 times the average flow at the mouth of the Mississippi River. Meteorologists call these structures atmospheric rivers, or ARs. They are relatively narrow, highly concentrated bands of moisture that stretch for thousands of kilometers, operating almost exclusively in the bottom 3 kilometers of the atmosphere. These continuous pathways are incredibly efficient at moving mass. Globally, they are responsible for up to 90% of all moisture transport from the tropics toward the poles. We cannot see them with the naked eye, but these synoptic scale currents are the primary physical mechanisms driving the Earth's water cycle. For the western United States, this transported moisture is a biological necessity. 30 to 50% of all annual precipitation in the West Coast states arrives in just a few of these atmospheric river events. But when these moisture-dense systems make landfall and stall over a single region, they routinely trigger extreme floods and mudslides. The Pineapple Express is one highly visible example. It's a specific type of strong atmospheric river that funnels intense, saturated air directly from the tropical Pacific near Hawaii all the way to the U.S. West Coast. A single weather pattern serves as both the primary defense against regional drought and the most severe, destructive threat to coastal infrastructure and property. This schematic shows how an atmospheric river gathers water. Low-level winds, the feeder airstream, pull moisture from the ocean into the warm conveyor belt. Inside, saturated air is forced upward along a frontal boundary. As it rises, it cools, condensing into intense precipitation. To measure exactly how much water is moving, scientists calculate IVT, or Integrated Vapor Transport. IVT measures water vapor in a vertical column by multiplying specific humidity by wind speed. Because vapor is invisible, meteorologists rely on complex calculations and global supercomputers to map it. By calculating the IVT, scientists can definitively quantify the actual density, wind speed, and severe weather threat of an approaching storm system. To get accurate data, the AR Recon program flies aircraft directly into the storms over the ocean to deploy dropsondes. Dropsondes are expendable weather reconnaissance devices dropped from aircraft to accurately measure atmospheric conditions as they fall to the surface. These physical sensors collect real-time temperature, wind, and moisture profiles. This corrects critical blind spots in models like the ECMWF. The ECMWF is a major global weather prediction system that frequently underestimates the actual moisture and warmth of these rivers in its lower troposphere models. If you're enjoying this breakdown of how we measure the invisible mechanics of global weather systems, take a second to like this video and subscribe to the channel. This chart maps corrected data onto the AR scale, categorizing storms from Category 1 to 5. The matrix plots IVT density against duration to provide a vital early warning system. It tells forecasters if a storm will be a beneficial, drought-busting rain or a destructive, hazardous flood. A Category 5 atmospheric river can pass overhead without harm if it stays over the open ocean. The danger materializes when the intense moisture transport makes landfall and collides with a physical barrier. Along the western coast, that barrier is mountainous topography. The elevated terrain forces the moisture-heavy air rapidly upward into colder altitudes. This mechanical lift acts like a giant hand, wringing the water out of the atmospheric sponge. If the weather patterns cause the storm to stall in place over highly vulnerable watersheds, that forced upward ascent turns into prolonged, extreme precipitation that overwhelms the local river basins. The landscape itself is the trigger. The steep terrain transforms a harmless channel of vapor into a highly localized natural disaster. Anthropogenic climate change is now altering the base physics of these systems through Clausius-Clapeyron scaling. This thermodynamic law dictates that the water-holding capacity of the atmosphere increases by about 7% for every 1 degree Celsius rise in temperature. This chart maps the Clausius-Clapeyron relationship. As the global atmospheric temperature on the x-axis rises, the total volume of water vapor that the air can hold and transport on the y-axis increases exponentially. Consequently, future atmospheric rivers will be significantly wider and longer. They will carry much higher IVT values, supercharging precipitation intensity when they finally hit land. With the atmosphere holding exponentially more water, the delicate balance of the West Coast water cycle is fracturing. The same invisible rivers that supply the region's drinking water are becoming increasingly volatile threats.